Hello everyone, welcome back to Nated Engineering once again. We are still on heat engineering science entry, and today we are doing an exercise. We're doing a question from the question paper that was written on the 30th of March 2017. It's question number 5, and we're going to start from 5.1, which says explain the law of conservation of energy. And the answer is energy cannot be created, nor can it be destroyed, but it can only be converted from one form to another. We go to the next question. 5.2. They say a piece of steel with the mass of 21 kg at a temperature of 89 degrees Celsius is immersed in 5 liters of water at 17 degrees Celsius. Calculate the final temperature of the water if no heat is lost. This is the information that we're given. We are told that we're working with steel and water. The mass of steel we're given as 21 kg, and the initial temperature, which is T1 of the steel, we're given is 89 degrees Celsius. We're then given the mass of water is 5 kg. We are also given the temperature as 17 degrees Celsius. Actually, the mass of water is given to us as 5 liters, but we know that 1 kg is equals to 1 liters. Therefore, this is also equals to 5 kg. That is why the mass is like that. You can notice that they did not provide us with the specific heat capacities of both the water and the steel, but there is a formula, or a table rather, on this question paper, which is the last page of the question paper. We have specific heat capacities for materials, or I think they are 6. Yeah, we have the specific heat capacity for steam, for water, for aluminium, oil, steel, and copper. So what we are going to do is we are going to look at the material that we are working with. In this case, it's water and steam, and then go to that table, extract the specific heat capacity of water, extract the specific heat capacity of steel. For steel is 0.5 kilojoules per kg, and for water is 4.187 kilojoules per kg. We are asked to calculate for what? T2, the temperature, the final temperature. We know that the heat transfer will take place up until the steel and the water are now having the same temperature. At that case, or at that stage, there will be no heat transfer. So we're looking for that temperature. And we know we are going to use what? Heat energy lost by the steel is equals to heat energy gained by the water. And that will be the mass of steel times specific heat capacity of steel times temperature difference of steel is equals to the mass of water times specific heat capacity of water times temperature difference. So we are going to substitute. Mass of steel is 21. Specific heat capacity of the steel is 0.5. Temperature difference. The heat energy is lost from the steel to the water. You can tell that by looking at their initial temperatures. Therefore, we are going to say 89 minus T2 is equals to the mass of water is 5 kg times the specific heat capacity is 4.187 times the heat the change in temperature, which will be T2 minus 17. Remember, the water is gaining heat energy, therefore T2 will be greater than T1. Now, we are looking for this. We have it on both sides of the equal sign. So our job now is to get these two on the same side of the equal sign and then take it as a common factor and make it the subject of the formula. So what we are going to do first is we are going to open this bracket. We are going to say 21 times 0.5 times 89. That will give us 934.5 according to my calculator. Then we're going to say 21 times 0.5 times negative T2. It's basically 21 times 0.5, which will give us what? 10.5. T2. It's a negative here. T2. This is not a multiplication sign. It's supposed to be a negative sign. Going to remove this multiplication sign. And have a negative. We do the same thing here. 5 times 4.187 is equals to what? To 20. .935 T2. 5 times 4.187 times negative 17 will give us what? Negative 355.895. We have the T2 here and we have the T2 here. So we're going to make sure that each term that has T2 are on the same side of the equal sign, which will give us something like this. .935 T2 plus 10.5 T2. It's equals to this, and this will then be on the equal same side of the equal sign as well, and that will give us something like this. 934.5 plus 3.5. This is 3. 355.895. So what we are going to do here is we are going to take the common we're not taking common factor, we're just going to add, because we have a positive sign. It's not a multiplication sign. We're going to add these two, and adding these two, we're going to end up with what? 30. 1.435 T2. It's equals to this, which will give us 1290.395. So what we have to do now is to divide both sides by 31.435, both sides, which will give us our T2 as this, which is 1290.395 divided by 31.435. And T2, I got it as 41.05 degrees Celsius. And we go to the next question, which is 5.3. Question 5.3 reads as follows. An aluminium bar with a length of 5.5 meters is heated from 293 kelvins to 423 kelvins. Determine the final length of the bar. We are given this information, and notice that there is no coefficient of expansion there. So we are going to go and extract the coefficient of expansion from the table that we have been talking about. We also used it on the previous question. So the coefficient of linear expansion of aluminium is 23 times 10 to the power negative 6 per degree Celsius. So we know final length is equals to original length plus change in length, and change in length is equals to original length plus, that's times rather, coefficient of linear expansion times the temperature difference. Original length is 5.5. Coefficient of linear expansion is 23 times 10 to the power negative 6. And the temperature difference, it's 130. And I got that our change in length is equal to 0.0616 or 0.016 meters. Therefore, the original length, since it's 5.5, it will be plus change in length, which is 0.016, which gives us 5.516 meters as our final length. And then from here we go to the next question, which is 5.4. 5.4 reads as follows. A steam plant produced steam in a boiler with a pressure of 1400 kilopascal and a dryness factor of 0.9. This wet steam now flows to a superheater where it is dried and superheated to a temperature of 210 degrees Celsius. If the specific heat capacity of superheated steam is 2.5 kilojoules per kg degree Celsius, determine the following. 5.4.1. The enthalpy of the dryness saturated, it was supposed to be dry saturated steam. And then the next question, they say the required enthalpy to change 2 kg of water into superheated dry steam. There's something that you have to notice there. The water, the enthalpy, the required enthalpy to change 2 kg of water. That one will most likely confuse people when they are about to do this calculation. So let's just do the calculations and see what I'm talking about. This is the information that we are given. They are saying the pressure of the steam is 1400 kilopascal. We know the first steam that is produced is what? Wet steam, and they are giving us the dryness factor as 0.9, meaning 90% of that mixture that we have is dry steam and 10% is still water. They are saying later that steam is passed to a superheater. A superheater is something that adds heat energy to the heat energy to the wet steam, And as we're adding heat energy to the wet steam, what do? We carry on the conversion of water into steam, and then after that process is done, the heat energy that is produced to the steam will now be used to increase the temperature of the steam. Now the temperature of the steam is increased to what? To 210 degrees Celsius, and we're given the specific heat capacity as 2.5 kilojoules per kg degrees Celsius. If you can go to the steam table, look for this pressure, you will notice that corresponding to this pressure, the saturation temperature is equals to, it says this one, 195, which tells us that this temperature is higher than this, therefore the steam is now superheated. So the first question, they say the enthalpy of the dry saturated steam, that is what? Hg 5.4.1. They are looking for Hg, which is from the steam table. Extract, I got that the value is 2788 kilojoules per kg. What's happening here? And then we go to the next one. They are saying determine the required enthalpy to change 2 kg of water into superheated dry steam. Notice that they are not saying the enthalpy required to turn the dry steam to superheated steam. In that case, we were going to calculate for HSS. If we already had dry steam and we needed the heat energy that is added in turning that dry steam to what? To superheated steam. Now they are saying the heat energy that is needed to turn water into superheated steam. Therefore, we are asked to calculate for H sup. H sup is the heat energy that is added from the beginning of the process up until the steam is superheated. And it is given by Hg plus specific heat capacity of the superheated steam times in bracket T sup minus the saturation temperature. This is 2788. Specific heat capacity is 2.5. 210 minus saturation temperature, which is 195. So we are going to use the calculator here. I got that our answer is 2825.5, and the SI unit is kilojoules per kg. Why is this kilojoules per kg? Because the values that we are extracting from the steam table, they are an SI unit of kilojoules per kg, meaning we are only calculating for the heat energy that is needed by 1 kg of water or steam. The mass that is the values that are on the steam table, they are for a mass of 1 kg. That is why our answer here is also in kilojoules per kg. But remember, we are told from this question number 5.4.2, that we are to calculate the required enthalpy to change 2 kg. They are giving us the mass of 2 kg. What then do we do? If this is for 1 kg, then we have to what? Say times 2 to this value, so that we get the heat energy that is required by 2 kg of water. And I got that our answer is 5651. It's kg. Now it's no longer it's kilojoules rather, no longer per kg, but it's just kilojoules. And that is what they asked us to calculate for, which is that brings us to the end of our lesson. I will see you on the next one.